This is the measurement lab by Navi and Monica. Our hypothesis was that smaller macromolecules moved faster than larger ones in the electrophoresis gel. Our first step is to prepare the agarose gel. In the lab, we're making a 1% agarose gel, so we use the equation shown on the left. What we did was basically a proportions, so x over 30 is equal to 1 over 100, which consequently is equal to 0.3 grams of agarose that's needed to make this gel. TAE is the running buffer in this experiment, and it is used because it helps dilute agarose. Since it was in a stock solution, we had to use the formula shown on the left to calculate the correct amount of TAE in the experiment. You can see the pictures in my presentation that show there's one picture with a large beaker which contains 380 milliliters of deionized water and one with 12 milliliters of deionized water. That equals 392 milliliters of deionized water for the solution and 8 milliliters of TAE for the solution. You can see in our formula how we solve these numbers. We had a formula called mass 1 times volume 1 is equal to mass 2 times volume 2. We substitute in numbers. We say 50 times the unknown volume is equal to 1 times 400. The volume is after the calculations, the volume is equal to 8 milliliters for the TAE, and the volume of the deionized water is 392 milliliters. Okay, next we set up the electrophoresis casting tray and insert the comb firmly. Then we pour the agarose solution into the electrophoresis and wait for it to become a gel. You can see in my picture, the orange arrow points to the comb in the electrophoresis casting tray, and inside of it is the agarose gel, which will become the solution that is pointed to by the green arrow. Okay, then once it becomes a gel, the agarose, we take out the comb and we pour in the TAE. There are now wells where the comb once was, and those wells are actually small indents. You can see them by what the orange arrow is pointing to in my picture. Okay, we were working with 5 samples in this experiment. The xylene cyanol, I was not sure how to pronounce that, the bromophenol blue, the orange G, the safranine, and also one was just a mix of all the dyes. Okay, the loading dye was a 5x solution and the 4 dyes were 1x solutions. To figure out the appropriate amount of solution we had to use the formula that's showed on the next slide. Okay, we use the same formula as before. Mass 1 volume 1 is equal to mass 2 volume 2. To find the volume of the 1x dye, we multiply 1 by the unknown volume is equal to 0.25 times 20, and the volume is equal to 5 microliters. And then the volume of the deionized water is 15 microliters. The volume of the 5x dye would become 4 microliters, and the volume of the water would be 16 microliters. And you can see that all listed in the chart right here. You can see the microliters and the water. Microliters for the water and for the dyes. How we micropipetted. We basically we did all the appropriate techniques needed for micropipetting. We used the appropriate micropipette for the volume that we needed. We adjusted the volume to the correct settings. We filled the micropipette up slowly. We didn't just release the button after we were done filling it. And we stored the micropipette at its highest volume setting to make sure that there isn't a lot of pressure on the springs. We did not drop the micropipette and fill the barrel with the micropipette with the liquid, and we never exceeded the micropipette volume capacity. Those are all incorrect things to do with a micropipette, and they can break the micropipette, and those are very, very expensive instruments. This is how we micropipetted water. You will notice that we used all the appropriate techniques. We very slowly pulled the lever down. We did not pull the button down all the way. And then very slowly we brought it back up. We didn't just release the button. We then placed the water in or any kind of solution into the appropriate canister. And once again, very slowly we're inserting and taking away. And you'll also notice that we're holding the micropipette properly. For loading our samples, this is how we loaded dyes into the electrophoresis casting tray, into the wells. Notice once again we're using all the appropriate techniques for micropipetting. Very slowly. We don't want any kind of inaccurate measurements or anything to happen to the micropipette. Very steadily we have to put the micropipette's contents into the well. We don't want to move around a lot, or else the water, dye or the solution will just not be in the well, and then we'll get an inaccurate uh, experiment. Alright, and then after that you can see the dyes in the well of the electrophoresis after everything was done. After we placed all the dyes into the wells. And then we turned on the electrophoresis thing at 50 volts for 20 minutes. And then after that you can see our conclusion. As you can see, according to the picture, the gels moved according to wherever they felt more, wherever they were more attracted to. These all were negatively charged, so they moved to the positive side of the electrophoresis. And this was negatively charged, this was the safrarin, therefore it moved to the positive side. The ones that were negatively charged were the xenocyanol, the bromophenol blue, the orangey, and the mix of all the dyes. The positively charged dye was safrarin. Our hypothesis was correct. The smaller particle dyes did move faster than the larger ones. And this was our entire presentation, and thank you for watching.